Faculty of Art and Science, and at CETER, Canadian Institute for Theoretical Astrophysics. So I'm new to the FRB community, so today it's a really great honor to be here in Taiwan, my first visit. And at the same time, I hope to kind of contribute my expertise on thinking about how information is encoded onto the radiation we receive, particularly thinking about polarization in radio band. Because the good news is we know FRB, they're usually for those we detected, particularly with repeaters, they are highly polarized. The question would be like why they are polarized and what are the emission mechanism. But at the same time, we also need to think about as the light propagate down from the emission all the way to the point we receive it, what happened during its propagation. So this will be what I meant by polarized radiative transfer. I will help everyone to navigate in this field. So just like Renpei's talk, he showed a lot of really good result of FRB polarization. I'm just adding a few plot that I saw from a science paper from Plan. This is showing for repeating FRB. And you can see what we can measure is apart from intensity profile, we can also actually get the polarization angle, how it changes over the pulse, and also the frequency and time plot. And this plot, also from the same paper, actually show a pretty good summary of the detection from different telescopes in terms of how the strength of rotation measure changes against its degree of linear polarization. So rotation measure concerns about linear polarization, and with this sort of plot, we start to see actually FRB is the property really diverse. Some of them are kind of more showing little linear polarization, if you can see my cursor over there at the corner. But some are highly linearly polarized. In terms of the RM strength, it also have a great scatter. So to understand what is going on, I think we need to also bring in the polarized radiative transfer understanding. And it is key when we think about cosmic messenger. How do we bring theoretical studies and observational data together? Without thinking what happened, what information got encoded to radiation, we're definitely missing a big part of it. So understanding how information is encoded to the cosmic messenger we receive is what radiative transfer is about. And because we look into polarization, that's polarized radiative transfer. And if we think about polarized radiative transfer in an expanding universe, put in the context that we live in an expanding cosmos, therefore substances and magnetic field within it also get involved. So that's actually what I meant by cosmological polarized radiative transfer. Because FRB extragalactic, and we may be able to push higher to higher redshift. So this also gives us an extra handle. So it's on top of intensity, now let's also think about polarization and also think about what it offers us. And I think in many talks, people talk about rotation measure as well, which concerns about linear polarization. I will unpack it a bit, put it in the context of polarized radiative transfer. I will use the acronym PRT, because it's quite hard to always say polarized radiative transfer. So here we go. What is polarized radiative transfer? Basically, let's think about our observable. We have IQ-UV, the Stokes representation of our light. All the properties of the radiation is captured there. And that's how we actually define the polarization angle over there. You just think about the UQ, and then you can kind of derive the polarization angle from there. And we have been talking about rotation measure, which really stems from physics of Faraday rotation. So if you have a linearly polarized light passing through a magnetized plasma, so the rotation, there's a rotation of the polarization angle due to the circular bifringes. So the left-handed and right-handed wave would travel at different speed through this magnetized plasma. And then what happens is you will measure the amount of the rotation, how much the angle changes, and want to invert back to the physical quantities here in terms of how much free electron density you have and the line of sight component of your magnetic field. So rotation measure has really been the workhorse that we kind of use our rotation measure to understand what happened to the source, the immediate environment, and the intervening media. But then rotation measure is really concerning Faraday rotation. But what actually imprint to the radiation properties, IQ-UV over there? So this is a full equation. So apart from Faraday rotation that determine your radiative properties in terms of QU. Other processes can do that too. In terms of signature radiation, you can have emission over this time here. You also have actually absorption, which is bracketed in blue there. And if you look at QU, the Faraday rotation coefficient will convert Q and U, and the Faraday conversion is the conversion between circular to linear polarization, vice versa. So basically, all these processes determine the radiation properties that you're going to measure. And the ds there is just like as the light pass through its propagation path, how it interacts with different baryons, and then got determined in what we observe. So what we are observing is IQ-UV, and they are all frequency-dependent processes. So we have to think about actually why we see the frequency behavior of our signal as we see that. And put it into context, here I'm showing just a background galaxy. It could be fast radio burst host galaxy or anything. But if you have a highly linear polarized light pass through a foreground media that can Faraday rotate, you'll see the angle changes. But as I mentioned, what determines the signal is not only Faraday rotation. There are other processes at play. Then the question is, which one is dominant? And could we kind of single out Faraday rotation? Just thinking about the Faraday rotation thin approximation that we saw in Yuanpei's talk. Can we always do that? So this is actually what is usually referred in the magnetic community, the Faraday thin approximation. You have a source that emits, and the foreground one, a single source, is just Faraday rotating. And then you can kind of get the IQ-UV. So the rotation measure in that sense gives you a very explicit inference of what this property would be. But at the same time, in physical situation, we still don't know what the progenitor and the host environment of all kinds of FRB are. So it could be also not only a Faraday rotating medium, but as well as self-emitting medium. The Faraday rotating medium can also self-emit. So if we want to do a proper job, we can't just go to a rotation measure, which is derived from the PRT. It really stems from that root. But you have to switch off absorption, emission, and conversion to derive that. So that really put us to think about, moving beyond from rotation measure, how do we interpret the signal? Rotation measure is great, but at the same time, it has its limitation because of the assumption that went into deriving that. So this is kind of one of the quick plots showing if you have a really clean NE source, actually the change of the polarization angle really have the wavelength square dependence. But it's all the FRB sources always follow this wavelength square dependence. That's the question I have for people who work on data. And when you deviate, what we should do, maybe we should think about polarized radiative transfer. So tomorrow, from Alvina's talk, we will hear more about rotation measure and quantitative assessment for that, like the physical basis, when it fell, when it's good. And we actually also derive a more general expression for rotation measure, not only accounting for thermal electron population. You can also have non-thermal, for example, non-thermal signature radiation that kinds of population that emit in a power law sense. So this is the more general expression for that, but still, remember the assumption that went into deriving the RM really have to switch all these radiation processes off, considering solely the Faraday rotation. And let's think about the general picture we are encountering here with FRB. So once it emits, it may transverse through different media. And remember, when it transfers through one medium, the kind of condition it has becomes the initial condition for the next stage. So for example, from the FRB host environment, then it propagates to the IGN. And then eventually we encounter our own galaxy, our ISM, and then got detected. So basically, you really have that order information imprinted on your radiation. But then if we use RM, which is just the integral, I just showed you, or we see from Yuanpei's talk, an integral, what it does, it erases that information. You're really projecting that information out. So hopefully, by telling you or showing everyone navigating in polarized radiative transfer, let's think back what the radiation that we receive encodes information. Thanks. And as I said, like for radiative transfer, knowing the distance is important. So I think from observation, if we eventually improve to get better and better in terms of localization on the sky, but also getting redshift information, that will really be super helpful. And on cosmological scale, this equation actually can be stemming the propagation path in terms of redshift. And there's also global event you have to take account. Because as the universe expands, the radiation wavelength also gets stretched. And remember, all the radiative transfer processes I mentioned, they're all frequency dependent. So we actually need a good account for this global effect that stretch the wavelength, the universe evolve, at the same time as local effect, the local interaction with your radiation and baryonic matter. And therefore I derived the covariant cosmological PRT, and that's what the equation looks like. I won't be bombarding you guys with how to solve this equation, but this is what you can do when you solve the equation in multiple ways. For example, you can solve for one way, you can also fire many beams and solve for pencil beam calculation, get a map out, and you can also do ray tracing in all sky setting. So there's a tool like this. I think directly advances us to the level like, oh, we can move beyond rotation measure when we need to. So let's think about how eventually we use our data, we use our theoretical understanding, adding a bit of radiative transfer thinking into tackling the problem we are facing now. So from observation, we really see IQUV, we can derive the polarization angle, the degree of polarization in terms of linear, circular, and also in terms of total. When we see different frequency behavior.
Thanks for Q&A.
Okay, cool, I'll just quickly conclude. And different variation. Let's put thinking back to PRT. And this one slide is just to show if you see some sign changes, sign flip in your IQUV, not sure why is it. I think there's two papers you can refer to. I wrote that appendix, it was very painful, but I'm happy to talk about that more. But it's more on the sign flip when you see it in B, in U. And there's also a good paper talking about the sense of our rotation. So this is my summary slide. Hopefully, when we one day will successfully bring together both theoretical advances and observational advances, let's crack down on the problem. Actually, why we see what we see. Think about radiative transfer, polarized radiative transfer, or sometimes in cosmological sense. Thank you.
Okay, thank you, Jennifer. Are there any questions? Okay, two questions.
Such a radiative transfer has been discussed in the context of AGN, and in that case also it's a cosmological travel.
Yes.
What is the new point of this formulation?
The new form, in terms of the CPRT, that is covariant in the sense, I'm not too sure how the AGN people did it, but whether they use this formula or this one, this is way more usual, but usually it happens for local medium. So I need to double check what the AGN works have done. But to the best of my knowledge, the cosmological covariant one, yeah, I was the one who did it. And that's actually covariant radiative transfer, but in black hole setting in curved space-time. But that's another contest.
Okay, thank you for the very nice talk. Just a quick question. Do you have any idea about decoupling the cosmological, global or the local effect that you mentioned?
When you said decoupling, I guess it's to single it out?
Yes.
I think that needs actually more forward modeling to really understand what the local medium does to PRT, then put into cosmological sense. So you can do it locally with just PRT, and then now you can put this medium, for example, at different redshift, and then you can add more components to it. Then you can, by that, just single out how much actually is because of the cosmological effect. Because why I suggests this approach rather than just using your Rn divided by 1 plus s squared. Because many things are co-evolving together. If you just do that simple correction, sometimes you may be missing out the evolutionary thing that happened. So yeah, this would be my approach to single that out, and it can be done.
Thank you.
No problem.
Okay, let's thank again to Jennifer. Thank you so much.
Thank you.